Hello students, we're going to solve numerical problems of this first chapter 1 of class 12, and these numerical problems were asked in AHSEC final examination under Assam Higher Secondary Education Council. So before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you, right? And stay connected. Okay, so now let's start. So here you see this is the first problem we're going to take here. So there's an electric field is given. Okay, we need to calculate the electric flux through a surface area. This is the area of the surface, and that surface is in YZ plane. Okay, so this was asked in 2014. Okay, Assam Higher Secondary Education Council AHSEC final examination in 2014. Okay, so now you see, so there is the electric field. So this is the electric field, suppose, which is given by 3I cap plus 6J cap plus 4K cap, right? So this is the electric field, and let me take, this is x-axis, this is y-axis, and this is the z-axis, suppose, and in YZ plane there is a area. That area is equal to 20 centimeter square. This area is equal to 20 centimeter square. Okay, so what will be the direction of the area vector? Direction of area vector is always perpendicular to the surface, right? So if this plane is on YZ plane, then the area vector should be along x-axis. Okay, along x-axis. That's why we're going to write area vector A, that's going to be 20 I cap centimeter square. Okay, and if you convert it into meter, then it's going to be 20 into 10 to the power, if you convert it into meter square, then it's 10 to the power minus 4 here meter square. Okay, and this is the electric field. Just I have drawn like this. We don't know in which direction it is lying. Okay, so exactly, so this is the electric field. So here we have electric field E is equal to 3I cap plus 6J cap plus 4K cap, and the area is nothing but 20 I cap centimeter square. So let's convert it into meter square. 20 into 10 to the power minus 4 I cap meter square, and we know that flux through the surface whose area is 20 centimeter square, that's going to be given by phi is equal to E dot A, right? E dot A. Let's find the dot product. So phi, that's going to be equal to, so E is this one. Let me write this one here. This is the E, and area is 20 into 10 to the power minus 4 I cap. So dot product of electric field and this area vector. Okay, so 3I cap 20 10 to the power minus 4 I cap, that's going to be 3 into 20 into 10 to the power minus 4, and we know that I cap and J cap, I dot J and I dot K becomes 0. So that's why this is going to be equal to, so let me write here, flux phi, that's going to be equal to 3 into 20 into 10 to the power minus 4, so Newton meter square per coulomb, right? So now that is nothing but 16 into 10 to the power minus 4, and you can write 6 into 10 to the power minus 3 Newton meter square per coulomb. So this is the answer. So now let's move on to the next question. So here you see, so this is the next question. Calculate the magnitude of electrostatic force between a proton and electron separated by a distance of 0.5, there should be a unit. So let me take this. So there must be a printing mistake. Let me take this unit is centimeter. I don't know what was the unit in the original question paper, but the book from where I have taken this question, in that book there must be a printing mistake. Okay, so let me take this centimeter. Our motive is to learn the method. Okay, so just let's try to solve this. We need to here also given that the magnitude of charge of proton and electron is given. Actually, though here it is given, but you should remember this. What is the charge of electron and proton? Okay, both same but opposite in nature. So charge of electron and proton, each of charge 1.6 into 10 to the power minus 19. The magnitude of charge is given 1.6 into 10 to the power minus 19 coulomb, and they are separated by a distance. 0.5. Let me take this one as centimeter. If it is centimeter, then 0.5 into 10 to the power minus 2 meter, right? So then so what going to be the force between the electron and proton? Therefore the electrostatic force between the proton and electron is given by, so let me write here, F is equal to K QP into QE divided by R square. We know the value of K, that is 9 into 10 to the power 9 into QP and QE both is equal to 1.6 into 10 to the power minus 19 coulomb. So just wait, give me a second. So 1.6 into 10 to the power minus 19 coulomb, right? So divided by R square. R we have taken 0.5 into 10 to the power minus 2 whole square. Okay, so now you see 9 into 1.6 into 1.6 and 10 to the power 9 minus 19 minus 19, 9 minus 19 minus 19, right, divided by 0.5 square means 0.5 into 0.5, 10 to the power minus 4, 10 to the power minus 2 whole square, that's going to be 10 to the power minus 4. So here you see, after decimal there is one digit, there is also one digit. So total in the numerator 2 digits after decimal, here also total 2 digits after decimal. So we can remove the decimals, okay, without doing any change in the in this values. Just you can directly remove the decimals, because in the both numerator and denominator we have. So first let me calculate this. Minus 19 minus 19 minus 38, and 9 minus 38, that's gonna be minus 29 minus 29, and there is 10 to the power minus 4. So here it's gonna be plus 4. So if that is the case, then it's gonna be minus 29 plus 4, that's gonna be minus 25, right? Minus 25, and here 5 into 5. Okay, that's what we will have, right? So if you multiply and divide, then what you gonna have? So you're gonna have approximately 92.16 into 10 to the power minus 25 Newton. Okay, and if you write the decimal here, that means if you write it in scientific form, then it's gonna be 10 to the power minus 24 Newton, right? So that's gonna be the answer. Okay, if this is in centimeter. Okay, if it is not given in centimeter, then the answer will be different. Okay, so hope you have understood this. Now let's move on to the next question. So before we solve the next problem, just this is my Insta ID. If you want to follow me, then you can follow me. Oza Loikajip 123, right? This is my Insta ID. You can follow me. Okay, so before we start the next problem, if you want to follow me on Insta, you can follow me. This is my Insta ID, Oza Loikajip 123. This is my Insta ID. Okay, so this is my Insta ID. You can follow me, okay, on Insta. So now let's solve the next problem. So 2-point charges 0.01 microcoulomb and minus 0.01 microcoulomb are placed 20 centimeter apart in vacuum. Okay, we need to calculate the magnitude of electric field intensity at the middle point of a line joining the two charges and mention its direction. Okay, so also we need to mention the direction as well. So here first let me explain the question. So there are two charges. One charge, this is a Q1. Just wait. So this, let it be Q1. There is another charge, let it be Q2, and their magnitudes, these two charges are 0.01 microcoulomb and another charge is minus 0.01 microcoulomb. So both are equivalent, opposite in magnitude, equal in magnitude and opposite in nature. So we need to find, what do we need to find? We need to find the field intensity at the middle point of this line joining these two charges. Okay, so what going to be the electric field here? Okay, so now you see, so this line is suppose along x-axis. Let me take this is along x-axis. Just do it. Let me take that way. This is along x-axis, positive x-axis. Okay, now this is positive charge, this is negative charge, right? We know that from positive charge, electric field, direction of electric field, it is radially outward. So direction of the electric field at this point due to this positive charge should be towards that should be away from the positive charge. That means along x-axis, along positive direction. And we know, and due to this negative charge, so this should be inward, so towards the negative charge. So that's why electric field due to the negative charge is also in the same direction at this particular point, because this is positive charge, you can see this is negative charge, and this is the point here. Electric field due to this one, that should be in this direction, and electric field due to this negative charge should be also in this direction, because from the positive charge it must be radially outward, and in case of negative charge it should be inward. So at this point for both this and this, the electric field direction should be in the same direction, that is positive x-axis. Okay, so that's okay. Now let's find the electric field at this point. Okay, so now you see, first let me write the charges. Q1, that is 0.01 microcoulomb. Okay, so 1 microcoulomb is 10 to the power minus 6 coulomb, so that's why we can write this one as 0.01 into 10 to the power minus 6 coulomb. Okay, so if you write this one as 1, then it's gonna be, just wait, let me rearrange it, then you can write 10 to the power minus 8 coulomb, right? okay, or 1 into 10 to the power minus 8 coulomb, same thing. And Q2, that gonna be same, but here sign is negative, that is only different here, but magnitude of the charge is same, Q1 and Q2 both, right? Magnitude of the charge same, right? So now you see electric field at this middle point. We know that electric field due to a charge q at a distance r, electric field is given by its magnitude is given by k q by r square, right? So electric field due to the positive charge at this midpoint, okay, and these two charges are separated by 10 centimeter, right? 10 centimeter distance, this is given. So distance between the two charges is 10 centimeter. So if you convert it into meter, that's going to be 0.1 meter, right? So now you see, let me take this point is A, this point is B. So let AB be the line segment joining Q1 and Q2, which is along x-axis, and let us take here C is the midpoint, C be the midpoint of AB, right? Of AB. Now let me solve the next part here. Let me continue from here. Okay. So net electric field at C, that's going to be given by electric field, net electric field at C, that's going to be given by electric field due to the positive charge at C and electric field due to the negative charge at C, right? And here you see, as the magnitude of each charge same, right, but opposite in nature, and as this is the midpoint, right, as this is the midpoint, so that's why, so electric field, strength of the electric field due to both charges will be same. So we can say that just wait, before writing this net electric field, let me mention one more thing, that electric field due to positive and negative charge both, their magnitude will be same. So that's going to be K into, so here magnitude of charge is 0.01 microcoulomb, so which is nothing but we have got 10 to the power minus 8 coulomb, right, divided by R. So here we have to take R by 2, that is equal to 10 by 2 centimeter. So divided by, this is divided by 2, and then it's going to be equal to 0.05 meter, 0.05 meter. So it's going to be equal to 0.05 square. So this is electric field, so that's why its unit should be Newton per coulomb, right? So hope you have understood this. So this should be the magnitude of electric field due to each charge at the point C. So therefore net electric field at C, so that's going to be equal to sum of E positive plus sum of E negative. That means electric field due to positive charge and negative charge, as both are same in magnitude, and that's why here you see So we are adding these two because direction direction of E positive and E negative are in the same direction, so this should be added, their magnitude should be added. So you can write simply 2 into this magnitude. Here we have taken this one, 2 times of this, right? So that's what we're gonna get, right? So now let us replace the value of k, put the value of k, so which is 9 into 10 to the power 9 into 10 to the power 9, right, into this Newton per coulomb. So if we calculate this, then that's gonna be approximately so hope you can do the calculation by yourself. So it should be 72 into 10 to the power 3 Newton per coulomb, right? So if you want me to show you the calculation, let me show it. First take the screenshot. I'm gonna clean this part. So just take the screenshot, pause the video and take the screenshot. So let me clean this part now. Just wait. So here you see, just wait, let me bring it this side. So here you see what we're gonna have, 2 into 9 into 10 to the power 9 minus 8 divided by 0.05 square, means you can write 0.05 into 0.05, right, 0.05 Newton per coulomb. So let's remove the decimals from here, before 2 digit, total 4 digits. So in that case here we should add 4, right? So hope you have understood this, because we had here 0.05 and 0.05. so if you multiply here 10 to the power 4, then you can remove the decimals, okay, then you're gonna get 5 into 5, okay, and 10 to the power this into this, that's gonna be 10 to the power this, right? So if that is the case, 2 into 9, that's 18 divided by 25 into 10 to the power, that's gonna be 5, right? And if you make this 10 to the power 5 like this, 10 to the power 2 into 10 to the power 3, you can write this way. Then 25 cancels 10 square, means 100, that is 4 times, right? Then if you multiply 18 and 4, then you're gonna get 72 into 10 to the power 3. This is Newton per coulomb, right? So this is what we have got here, okay? So if you write this one in scientific form, then 7.2 into 10 to the power 4 Newton per coulomb, right? So hope you have understood this. So it is direction of net electric field is along positive x-axis, okay, positive x-axis according to our diagram, okay, positive x-axis, positive x-axis. So hope you have understood this. So that means that electric field we have got, if you write this net electric field in vector form, then E net, that's going to be equal to 72 or 7.2 into 10 to the power 4 I cap Newton per coulomb, if you write this one in vector form. So I cap is the unit vector along x-axis, right? So this is in vector form. Okay, now let's move on to the next question. So now you see, calculate the electric force between two charges, 1 coulomb two charges, 1 coulomb charges, okay, placed at 100 centimeter apart. Value of epsilon naught is given, that is 8.854 into 10 to the power minus 12, and let's find the electric force between 1 coulomb charges. So here Q1 and Q2 both is equal to 1 coulomb. Q1 and Q2 both is equal to 1 coulomb, and they are separated by a distance of 100 centimeter. So that's going to be 1 meter, right? 100 centimeter is nothing but 1 meter, right? So now electric force between these two charges, electric force, just wait, electric force between the two charges that's going to be equal to F Q1 Q2 by R square. So K is nothing but 1 by 4 pi epsilon naught, right? 1 by 4 pi epsilon naught. Here though the value of epsilon naught is given, so we know the value of this 1 by 4 pi epsilon naught. So instead of putting epsilon naught is equal to 8.854, then again putting the value of pi 4, that's going to be very lengthy. So as we know the value of this quantity, so that's why we're going to write directly 9 into 10 to the power 9. Q1 is 1 coulomb, Q2 is also 1 coulomb, R square is nothing but 1 meter, so 1 square. So this is Newton. Okay, this is force Newton. Just you can add one more step here. So as the value of epsilon naught is given, so you can add one more step. 4 into 3.14 8.854 into 10 to the power minus 12, 10 to the power minus 12, then into Q1, value of Q1, Q2 both 1, and R square, that's going to be 1 square. So you can show this step, okay, that will be better as the value of epsilon naught is given. Then so we know this value is equal to nothing but this one, so just you can put directly without any calculation, okay? Just don't skip this step, okay, as this value is mentioned here, okay? So this 1 into 1 by 1 square, that's going to be 1, right? So our final answer is this, very simple, 9 into 10 to the power 9 into 10 to the power 9 Newton. So this is the electric force between the two charges. So hope you have understood this. Let's move on. So there is another question which is similar to the last one, okay? Here the magnitude of charges are given 1 into 10 to the power minus 7, 10 to the power minus 7 coulomb, okay, and 30 centimeter apart in air, okay? So very simple, Q1 and Q2 both equal to 1 into 10 to the power minus 7. We need to take the magnitude only here. So R is 30 centimeter. So if it is written in meter, then divided by 100, that's going to be 0.3 meter, right? And the force between these two, that's going to be again Q1 Q2 by R square. So that's going to be equal to 9 into 10 to the power 9 into 1 into 10 to the power minus 7, again 1 into 10 to the power minus 7 divided by 0.3 square, okay? So that should be Newton, unit should be Newton. So now let me continue next part from here. So F is equal to 9 into 10 to the power 9 minus 7 divided by 0.3 square, that's going to be 0.09. And if this is the case, then if you write this one as 9, then you can write here 10 to the power minus 2, okay? So 9 gone, we're going to have 10 to the power again here, what we're going to have, 10 to the power that's going to be minus 5 plus 2, right? 10 to the power minus 5 plus 2, that's going to be 10 to the power minus 3 Newton. So that should be the force. So this is the answer. So let's see what is the next question. So here is Hope you know this definition. We are not going to give I'm not going to give the definitions here, just we're going to solve here numericals. Okay, so an electric dipole with dipole moment, this is not centimeter, this is coulomb meter. Okay, dipole moment, angle at 30, with the direction of uniform electric field, magnitude, calculate the magnitude of the torque acting on it. So here you see, suppose this is the uniform electric field. Let me take it. This is the uniform electric field E. Okay, and we have a dipole. So let me take, this is the dipole. This is the dipole, positive, this is negative, and its dipole moment is given, and dipole moment P is given. So magnitude of P is given, that is 4 into 10 to the power minus 9 coulomb meter, and magnitude of the electric field is given 5 into 10 to the power 4 Newton per coulomb, right? And magnitude of torque and the theta, this angle theta is given. So that means angle between P vector and E vector, that is given, that is equal to 30 degree, right? That is equal to 30 degree. So we know torque acting on dipole, tau is equal to PE sin theta, right? So P is given 4 into 10 to the power minus 9, and E is given 5 into 10 to the power 4, and sin theta is 30 here, and sin 30 is half. 4 5 is 20 into 10 to the power minus 9 plus 4, that's going to be minus 5. That half, that's going to be 10 into 10 to the power minus 5. If you cancel 20 by 2, then you're going to get 10 here, right? 10 into 10 to the power minus 5, that's going to be 10 to the power minus 4, right? So hope you understood this. And this is Newton meter. Okay, this is Newton meter. Torque, unit of torque is Newton meter, right? So now let's move on to the next question. So what is the net electric flux through a closed surface surrounding an electric dipole? Derive the expression for the electric field intensity both inside and outside charged spherical cell. So we have already done these things, charge expression for charge electric field due to charged spherical cell in the last video, I think. Okay, so first let me solve the numerical part. What is the total charge enclosed by the closed surface if the electric flux entering and leaving the surface is this and this? Okay, so inward flux in, that is 200, simply 20,000, you can say 20,000. So flux in is 20,000 Newton meter square per coulomb, right? And flux out is 30,000 Newton meter square per coulomb, right? And inward flux is taken as negative and outward flux is taken as positive, remember that. Okay, so net flux, if you add these two, then you're gonna get so minus 20,000 plus 30,000, that's gonna be 10,000 Newton meter square per coulomb, right? So that is the flux. So by Gauss law, this net flux So let me copy this one. Okay. Let me write it. Just wait. Okay. This net flux through a closed surface is 1 by epsilon naught times of the charge enclosed by the closed surface, right? So let me continue. Okay, here. So by Gauss law we get net flux is equal to Q by epsilon naught, where Q means charge enclosed. Let me write here Q enclosed. Okay, charge enclosed is this. Okay, Newton meter square per coulomb. So if that is the case, what we need to find? We need to find the total charge enclosed by this surface. So Q enclosed, that gonna be 10,000 into epsilon naught. So we know the value of epsilon naught is here, it is given. So use this value, then charge enclosed will be 10,000 means 10 to the power 4. Epsilon naught is nothing but 8.85 into 10 to the power minus 12. Okay, so we are calculating charge. So here now this unit becomes coulomb only from this state. Okay, coulomb. So then what we're gonna have? 8.85 into 10 to the power minus 12 plus 4, that's gonna be minus 8 coulomb. So this is the charge enclosed. Therefore the charge enclosed by the closed surface is 8.85 into 10 to the power minus 8 coulomb. So this is our answer. So hope you have understood this. So here is the next question. You are to bring two charges Q1 and Q2 from infinity to points represented by the potentials V1 and V2 in an electric field E if the distance between Q1 and Q2 within the field E is R. This distance between V1 and V2 is R. Total work done in assembling the configuration, and imagine an electric field E of 20 I cap and 30 J cap Newton per coulomb in space. Okay, the potential at the origin is 0. Find the potential at the point 2, comma 2. Okay, so here you see. So suppose, let us assume this way. This is the origin, suppose O. There is a point and there is another point. Here potential is V1, here potential is V2. From infinity we are to bring two charges. One is Q1. Q1 is being brought to this point where potential is V1, and the charge Q2 is being brought to the point where the potential is V2 from infinity, and distance between these two is nothing but R. Okay. Now you see here work done. Now you see, if there is a point where potential is V and Q charge is being brought from infinity to this point, then work done is given by Q into V. So you must know this. Okay, Q into V. Okay, so this is the basic knowledge that you should have to solve this problem. Okay, so now you see, therefore work done to bring Q1 from infinity to the point where the potential is V1, that is given by W1 is equal to Q1 into V1. Similarly, work done to bring Q2 to the point where potential is V2 is W2 is equal to, that's supposed to be Q2 and V2, but one more thing. So before you brought these two charges, here potential was V1, here potential was V2. Once you bring Q1 and you establish at this point, you establish this charge at this point, then potential at this point will be changed. Okay, V2 and V2 was initial potential, and after Q1 is brought to Q2, Q1 is brought to this point, so potential at this will be given by, you know that potential due to a charge Q1 at a distance r, that is given by what, K Q1 by r, right? K, that should be K Q1 by r. So that should be the potential due to Q1, right? And work done to bring Q2 from infinity, that should be V2 plus this potential. This is potential due to Q1, right? So this was the initial potential and this is the potential due to Q1, right? So that's why the work done to bring Q2, the point where potential, to the point where the potential is V2, is given by this. So here, don't write here similar, okay? Write this way. So what gonna be the total work done? Total work done to, in assembling the configuration So take the screenshot. I'm gonna clean this part. Yeah, just let me clean this part. The total work done, that's gonna be given by W1 plus W2, W1 plus W2. So Q1 V1 plus, if you multiply, then you're gonna get Q2 V2, then plus K Q1 Q2 by R. That's what you're gonna have. So this is the answer, right? So let me just write this here. Okay. So this is the answer, right? So hope you have understood this. And one more thing we need to find. So let me solve the second part of this question here. That is what? The potential at origin is 0. Find the potential at the point 2, 2. So here the electric field is given. That electric field E is given. That is what? 20 I cap plus 30 J cap. So here electric field is given. Electric field is given that 20 I cap plus 30 J cap Newton per Coulomb. And potential at origin, let me write here V0, potential at origin is 0, V0 is equal to 0. Potential at origin is given V0. So So we are to find the potential at V at 2,2. We are to find potential at 2,2. We need to find this, right? So I'm gonna clean this part. Just pause the video and note this part. Okay. So this is the first part of the numerical. Okay. So let me clean this. So now you see, we know that potential difference is given by minus integration from initial point to final point EdR. We know this. Okay. So here the initial point is V0. That means, so in our case, as we need to find the potential at 2,2. So in this case, our del V, in our case, del V is nothing but potential difference between the points 2,2 and 0,0. That means the origin. Okay. So that should be 2,2. Okay. Now you see, potential at origin is 0, so that's why del V is nothing but potential at 2,2, right? So potential at 2,2. This is minus 0, so potential at 2,2 is del V here. Okay. So potential at 2,2, that's going to be minus. So electric field is given 20 I cap. So this is x component. So we can write this integral like this way. Just wait. Let me show you one more thing. Just wait. Now you see, if the electric field is suppose Ex I cap. Let me take this one as this Ex I cap and Ey j cap. Okay. Then this integration EdR, that can be written as Ex dx, integration Ex dx plus integration Ey dy. We can write that way. Okay. So if that is the case, we can write integration 20 dx from 0 to 2, because one point is 0,0, another point is 2,2 here. Origin is 0,0, right? So 0 to 2, and then as there is minus, so we can write minus 0 to 2, and next component, y component is 30 here, 30 dy. That's what we can do, right? So if that is the case, then let me take the negative sign common, and so here what we can have, 20 integration of dx is x 0 to 2, then plus, after taking common minus, we have got plus here, 30, the integration of dy is y, so here 0 to 2, okay, 20, sorry, minus 20 to x 2 minus 0 and plus 30 into here y gonna be equal to 2 minus 0. So we have used the upper and lower limits. So here we're gonna get 40 plus 60, that's gonna be minus 100. So that is what we have got, right? 100 volt. So this is the answer. So hope you have understood this. So thank you for watching. See you in the next video. Stay connected. Okay.